Morning. Uh, Today we're gonna continue on working Simulink examples. Last time we worked a couple of examples. We solved a couple of differential equations, linear or nonlinear differential equation using Simulink. Today we're gonna. There's a couple more of these problems that are uploaded on Canvas under in-class problems. We wanna solve these. So let me share my screen and just let's jump on those. And today we're just gonna solve in this lecture. We're gonna just solve these a couple of problems, and that should do it for this chapter. And then the next lecture will cover a chapter. We'll move to chapter 11. Okay, so let's read this problem here. Consider the system of lifting a mast shown in figure problem 226. This 70 feet long mast weighs 500 pounds. The winch applies a force of 380 pounds to the cable. The mast is supported initially at an angle of 30 degrees, and the cable A is initially horizontal. The equation of motion of the mast is the 25,400 theta double dot minus 17,500 cosine theta, again, plus 2600 over Q, 626,000 over Q, sine 1.33 plus theta. So this is definitely a nonlinear differential equations because it has a trigonometric function of theta, and it has this theta double dot, and also Q in there. It is a function of theta as well. So definitely it's a nonlinear differential equation. It is extremely hard to solve this. There's no exact solution for this. So we want to create and run a Simulink model to solve for and plot theta t less than or equal to pi over 2. So a couple of things I want to do before, always when you want to, always want to solve for the higher order equation, derivative. So in this case, theta dot, I'm just going to do theta dot here, double dot, is equal to 1 over 25,400 times minus 17,500 cosine theta, plus 625,000. Let me just make some room here. Right. So cosine theta plus 625,000 over Q sine of 1.33 plus theta. Okay, close the bracket. So in this case, what we want to do, we want actually to create a, since this is a function of theta, we're gonna create a return back to theta double dot with this function right here, that big function here, f of u. So all right, so let's do that. Let's do that. And so let me just make sure I bring this equation here this way, and let us solve. Yeah, let's just go in here. One, let me minimize these because we don't need all of this here. And also close window. minus, and also close window. And you know what? Let me just go open this one here. Simulink. Let's just here. All right. So let's go home here and let's open Simulink. So going to do similar what we did earlier, just that f of u, that function, it's going to be a little bit messy because it's a long function. Let's for this to open, it's taking some time to load. All right, so this is it. We're going to create a blank model, and yeah, we're going to try to fit it in here. All right, so the first thing we want to do in this case, you know, you can start from left to right, whatever you want. It doesn't really matter. Since we know we're gonna integrate twice, and let's just make sure that if we go in here, want to see if there's initial values for theta double dot or theta dot. There is nothing, so I'm just gonna keep theta dot. 0 is 0 and theta 0 is 0. So there's no initial conditions are zeros. So let's start with the integrator here. So I'm going to do two integrator and another integrator also. All right. So both of these, if I click twice, it has a 0 initial condition. So we don't have to change anything. So let's just, we know that we have to integrate twice to get to theta, right? Theta double dot. And so what we want to do is, let's get a gain here, 1 over 25,000. So gain, and that is 1 over 25, 400. Okay. So you can enlarge that one a little bit. So it is shown. Maybe I'll increase that a little bit. And let's just do sim out in here. Because we want to plot it in a, all right. All right, so now what I want to do, let me also connect this one to this. Since this theta is right here, so I want to form a function as a function of theta. So if I want to do, I'll just do here function, and let me double on this, and I'm gonna here enter that function. And remember, this function is a function. There's a cosine theta, there is a sine of theta, 1.33 plus theta, and q also is a function of theta. So so let's do that, minus 1.7. It's gonna be lengthy, but it's nothing, cosine of theta, or in this case u. We're gonna do this one as u. So let's do this one as u1. Okay. Okay. So we'll do that U1 and so 1700 cosine theta U of 1. Let's close the parentheses. And you have plus 62 to 5,000 divided, or let's just leave this one here. Let's do sine times sine. We'll leave the q later on, sine of 1.33 plus u1. Let's just keep this one lowercase. Okay, so that is divided by q. So let me close this parenthesis. And let us divide this by square root. I'm putting this value here, q, right there. So it's square root. Let me open a parenthesis. Just be careful when you enter those. It's 20 plus 1650 times cosine of 1.33 plus u1. All right, so let's close the parentheses, right? And yeah, that should take care of this one. Yeah, sine. Okay, so apply. Okay, all right. So that is, and I'm gonna actually flip this. So right click and flip block, and I'm gonna connect this. Remember, this is where theta, which is u in this case, u1. Now, this is what I need to right here. So if let me put that here. The reason why I put u1, you can just put u, that's fine, because it's only a function of a function of theta. But let us suppose that you have the right hand side is also a function of theta dot, okay, which is the angular velocity or the angular speed of that. So if you were to have that, you will call theta u1 and theta dot to be u2, okay? But in this case, we don't have theta dot on the other equation, so we're good just to for u1. And even if you just call it u, it would be fine. Okay, so that is it. Let me save that and save as example. Let's do this is 26 and save. And you know, let me also do a scope here. Scope, and let me connect that. Run it. Let's run it, and let's see the scope. I'm gonna actually try to do also the plot as well. Let's see here what we got here. Oh, basically, we got nothing in here, so something is not right. Let us see what's going on here. 1 over s, 1 over s, 1 over 25400. Do this here and see what's going on. I don't know what's going on. Why this is not canceled. Hmm. Oh, okay. Here we go. Let's see. Put the initial condition here. There is actually an initial condition. That is. Let's do this one. Let's read this. The mass support initially at angle 30 degrees. So initial conditions in this case is theta 0 is 30 degrees. So right. So here we're gonna do 30 degrees. That's pi over 6, pi over 6. And apply. Okay. And let's run now. Let's see what we get. Also nothing. So we got something is not right with the equations probably that we enter. So let us see what we can do to fix that. All right. I think I found a mistake here. There was actually one parenthesis that is missing at the end. So please, if you're doing this, just add that parenthesis. That was causing the problem. So that function, I told you it's long. You just have to be careful when you enter it. So we fix that. Let's do the calculation. So, and you'll see here that is the function theta. So that is a great non-linear differential equation solution. It really hard to do this numerically because there's no exact solution. If we were to plot this into MATLAB, remember this is where the sim out you see at the workspace. So what you can do, just do the plot, and in this case, since there's two, so let's do here. It's gonna plot two now. If we do that, if we go in there and plot out P out, out sim out, you're gonna most likely get a two plots. But let's see. Plot can only view single time series objects. So okay. So let's do out sim out 1. Yeah, let's do this one here. You know, actually, if you know, this is the 1, and sim out 2. Sim out 1 will plot theta, and sim out 2 will plot theta dot. Okay. Remember, you know, we might not get this because we have to do this as an array, but let me try it anyways, and we'll see if we get this. All right. So let's do this then. Let's go back to the problem. And when we do sim out here, make sure you don't do the time series to an array, and apply and hit OK. And now let's go back to MATLAB. Let's clear this. This is never used to be like this before they updated the system, and now you really have to be careful when you run sim out. So let's redo this again, and let's go back in here. So we have a new series of data, and let's do this again, and let's see if we can get, so exceeds array bounds must not exceed 1. All right, let's just plot 1 for now, and then we'll see why it is not. Let's do this here. Okay, so that is pretty much the same as this one here, the scope right there. Okay. All right. All right. So Let's do, there's probably two more problems, so let's do one. Yeah, let's do more. So again, just if you go back to that Simulink problem, that f of u, which is f of theta, is really the tricky part because it is a very complex equation, right? So let's open here and let's read the following problem. So this is a dynamic problem, spring mass system, mass spring system with damping as well. So this you have two masses and two springs, two damping system. And this is the equations of motion. M1 x1 double dot plus c1 plus c2 x dot 1 plus k1 plus k2 x1 minus c2 x dot 2 minus k2 x2. There's a couple of ways of doing this. You can do a free body diagram and for each mass and do the balance, or you can just use the energy equation in dynamics, and we learn how to do this. You know, the potential energy should be equal to the kinetic energy. And again, m2 x dot 2 plus c2 x dot 2 plus k2 x2 minus c2 x dot 1 minus k2 x1 will be equal to ft. Ft is the force with respect to time that's pushing on this mass m2. So if you took dynamics, you should be able to figure out this on your own, or physics too, I believe. So it's given us the masses, damping constants, and also the spring constants. Develop a Simulink model on this system, and doing this, consider whether to use a state variable representation or a transfer function representation of the model. So you should be free to use any one. We'll see which one will make sense. And then use the Simulink model to plot the response x of t for the following input. So we have three types of equations of that force. One is a linear force, t. The other one also another linear function, 2 minus t. And the last one is 0. And this is from t. The first one is from t 0 to 1, 1 to 2, and also when t is greater than 2. Okay, so we want to first use the, most likely I'm going to use the LTI system. So I want to come up with A and B, those matrices. So I want to rearrange this. So let us do this. Let me call Z. So first one is I'm going to call Z1. Yeah, maybe I'll just do it here. Try to, I don't know if it's going to fit, but we'll try to let it fit. So let's do Z1 first. It is equal to X1, which means that also Z2 is equal to X dot 1. Okay. And you have Z3 is equal to X2, and Z4 is equal to X dot 2. Okay. So the first equation that we are going to have, and we're going to come up with 4 equations. So let me do those equations here. Those equation in here. Okay. So the first equation that we are going to have is z dot, because we're going to, all these equations are going to be as a function of, so again, z. The first one is z dot 1, right, which is equal to x dot 1, right, which is equal to z2. This is the first equation. The second equation, all we're going to do, we're going to put everything z dot 1, z dot 2, z dot 3, and z dot 4. And this is how we're going to come up with the x dot or y dot or z dot in this case will be equal az plus FT or BU. So Z dot 2, I'm going to use this equation for Z dot 2, the first equation, right here. Remember, this will be Z dot 2. So we're going to put everything as a function of this one, right? Because this is Z2 is equal X dot 1. So Z dot 2 will be equal X, let me just do C dot double dot, or Z dot 2 here, will be equal X double dot 1. So I'm going to put everything as a function of X1. So Z dot 2, right? So I'm working on this equation, equation 1. So let me come back in here. So Z dot 2 is equal minus 4. I'm not putting all the mass and all these things, minus X dot 1 minus 5 X1 minus X dot 2. Okay, also plus 4x2. I'm going to put everything as a function of z. So z1 and z2. So the first one, my x dot 1, so that's going to be minus 4 z2, right? That's x dot 1. And minus 5 z1, right? x1 will be z1 minus x dot 2, which is minus z4. Okay, is that plus or minus? Yeah, this is plus. So plus z4. And the last one is plus 4x2 will be equal z3. Okay, so if you want to put it in a different form, you can just do this one as, again, this is z dot 1, so z dot 2 will be equal to minus 5 z1. Just put it in sequential here, minus 4 z2. Here. Okay, and plus 4 z3 and plus z4. So that is equation 2. Right, so this is these two equations so far. Now, what I want to do, we want to work on z dot 3, and we know that z dot 3 is equal to x dot 2, which is equal to z4. Okay, so that is z dot 3. So that is equation 3 here. One more equation, I'm going to go back to this equation here and put everything as a function of z dot 4. Remember, this is z dot 4 right there. So z dot 4 will minus x dot 2 minus 4 x2 plus x dot 1 plus 4 x1 and plus f of t. And that is minus z4 minus 4 z2 plus, sorry, 4 z3 plus z2 plus 4 z1 plus f of t. You can rearrange it in a ascending order, so that's 4 z1 plus z2 minus 4 z3, this is minus, and minus z4 plus f of t, and this is equation 4. Right? So for equation for knowns, so what we want to do is get the A. If I'm going to scroll down a little bit here. So A in this case, remember 4 equations. Remember the form here is z dot is equal to a times z plus d f of t, or in this case, bu, or yeah, this is f of t. Okay, so a is matrix 1 and b is matrix 2. So for a, we're going to expect 4 by 4 matrix. So if we scroll down a little bit, I guess I can't. Yeah, let me just work whatever space I have in there. So because I want to look at the equation. So this is A. So that's going to give you 0, 1, 0, 0, minus 4, 5, and minus 4, 4, and 1, 0, 0, 0, 1, and 4, 1, minus 4, and 1. Okay, remember, that's why we put them in an ascending order, Z1, Z2, Z3, Z4, so it's easy to pick up this. So, and this is A, B will be, in this case, 0, 0, 0, and f of t, and this end will be equal 1. Okay, so now we're ready to enter those in a LTI diagram inside the and if we want to only solve for positions, so in this case we do not have, so if we would just want the output to be x1 to be z1, right? In this case we can do c, in this case c will be equal to 1, 0, 0, 0, and d will be equal to 0. And that will give you only x1 equals z1. Okay, that's the output. Now, if you want more outputs, if you want z1 and you want z3, for example, or z2, then you have to change this to 1, 1 or 1, 0, 1 to get the other variables. So so let's do this. Let's do this. Since now we have all of the again, this one is z dot is equal, and that will be y is equal to c z plus d ft here. Okay, and remember, y is the output of z that we want. Okay, and we chose only we want to have z1. We didn't choose z2 or z3 or z4, but you can definitely get those as well. Remember, we have it's a 2 second order, and you have 2 variables. Again, x1 and x2, because you have displacement for these 2 masses. So you can get the displacement for mass 1, and also you can get displacement of mass 2. And if you go back and see exactly what we named, we said z1 is equal to x1 and z3 is equal to x2. So you are, if you were to find the displacement of mass 2, you want to calculate z3. If you were asked to find the velocity of that mass 1, you want to find z2, and same thing for z4, because z4 is the velocity of the mass 2. Okay, so that thing will change, your matrices will change, because in this case, if you go back in here, y will be, which is in this case x, x1 and x2, will be equal cz plus tf dt. But in this case, we chose only 1, 0, 0, 0, because only we're looking for only one variable, which is x1, right? Remember, y cz plus is equal to cz plus tft is the output that we want from solving the LTI equations. All right, so let's minimize that and just go to a new. So let's just go to a new one. Do this here. A blank model. All right, so let's see what we can do with this, because so we let's do this space. Yeah, state space here will be better to solve this problem. And let's see what we have in here. I'm just going to put that A matrix. So A matrix in here, open bracket, you have 0, 1, 0, 0. And then you have -5, -4, 4, and 1. Third row is 0, 0, 0, 1. Fourth row is 4, 1, -4, and 1. And we're going to close that. B, again, is, we said it is 0, 0, just to make sure, 0, 0, 1. So 0, 0, 0, 1. Was it? And C, we said it is 1, 0, 0, 0. So yeah, let's just do this one here. It's 1, 0, 0, 0. And D will be just 0. Okay. Initial conditions. Let's see what we have for initial conditions. So what do we have as a part? Initial conditions are 0, so we're just going to keep everything 0, zeros. Okay. Apply. Okay. For parameter B. Okay, I have made a mistake here. Let me take this one off and apply. Okay, so that is set for us. Now let's do the sim out as usual. So we do sinks, sim out, and swap it here. All right. And what I want to do is I want to see what's going on here with the ramp, because he asked us to use, look at this function, f of t for t between 0 to 1 is equal to t, 2 minus 2, okay, 2 minus t, and then 0. So you have 3 ramps. So I'm going to do first ramp here. All right, and the slope and the ramp, this is really important here to, we're going to set the slope for 1 and the start time to this to be 0, okay? So because 0 to 2, 1. And the initial output, let's leave it to be 0. That's the first ramp. I'm looking here, ft is equal to t, and the start time is 0, and the initial output is 0. So let us do that, and let's do another ramp here. And in this one, let me open that. we are going to do the slope. We're going to set the slope for this ramp. Uh, should be, so we start at from 0 to 1 at t, and then we're going to go with another slope. So that's going to be, the slope will be, in this case, 2 minus t, because we were going upward, then now we're going downward, so it will be equal to 2, right? Because we start, the slope will be positive, we're going upward, but then 2 minus t will be going downward. So this is what I am trying to say. So we are starting like that. So let's suppose we start something like this. And then now we're going to go like that, right? So between t, again, this is from 0 to 1, right? And now you have this one from 0 to 2, right? This is 2 here. And then here you have ft is equal to 0, so that will be something like this. So to go from this slope to this slope, we are going to have a slope of 2, and the start time in this case will be 1, right? Because, yeah, it'll be 1. Start time will be 1 here. 1. And initial output will be initial output will be 0. So that should do that for this. Now the last ramp. Now there's another way of doing this, which is easier. And we'll do. So the last ramp will slope will, which is for block 2, will be, in this case, we're going from to ft equals 0, so we're going straight. So we're moving 1, slope will be 1, and the start time in this case will be 2, and initial position will be, initial output will be 0. So okay, and I'm gonna do a minus here. Remember, and here it's 2 minus 2, so that's why we have the slope at 2. But so if we do a sum here, and we can do, let's hit this, we're going to do plus minus and plus in here, and hit apply. Okay, so so we're going to add this to this one, and the minus, because remember the slope is minus t, so we're going down, and now we go out from minus t to 0, so that is a t. Yeah, that's a slope of 1, and then we'll connect that. So let's do also scope here. Let's connect that as well. I always like to have the scope to see what we get. And let us save that one. So that one is, what is the name? What's 1035? So save. That is that. Let's see what is the result. So let's move this one here. Yeah, that looks good. Uh, so this is the displacement of mass one. Uh, so let's see here. All right. So if you were to, I'm gonna try to find another way of doing those ramps. I've done it before in a different way. Let's see here what we got as far as, so this is the placement of, uh, you know what, let's do that in the, so if we were to, let us suppose, let's go back to this side here. And if I were to plot also the displacement of mass 2, so how would I go about doing that? So remember, I set C here to be 1, 0, 0, 0. So I can probably do uh, something like this. Let's see here. C1, 4 by 1. Yeah, I'm gonna have to change C a little bit. All right, so if let me go back to the scope. So that is the displacement of mass 1. Let us suppose, like I said, I wanted to plot displacement of mass 2. So what do? So let me go back to the state space equation. And remember, C times Z plus T times FT is whatever output we want. So in this case, since I want Z3 in this case, which is X2, remember, Z1 is X1. Z2 is the derivative of X1, which is X dot 1. Z3 is X2, and Z4 is the derivative, which is the velocity of mass 2. So I'm going to go to this modify C because I do not want the velocity so of 1 for now. I'm going to try to plot it later on. And I want so I'm going to go set the diagonal of C, which is a 4 by 4 matrix. So I'm going to set it to be 0. And this is the diagonal value of row 3. And then row 4 will be 0, 0, 0, 0. Okay. And for D, since we change, remember, y is equal CZ plus DFT, so you have to change that one as well. And in this case, you just need to do 0 and 0, 0, 0, and close the bracket, okay? I have to put that because it's supposed to be 4 by 1 matrix. This is 4 by 4 matrix. I hit apply, and hit plus okay. And now, if you rerun it again, and you see you should get two plots, one for x1 and one for x2. You might tell me which one is x1 and which one is x2. This is why we're going to go to the sim out, and it will be easier for us because we know that the way it's going to be is going to be Z1, Z2, Z3, Z4. This is how it is arranged, and we're going to go back to the sim out, and we're going to digest and inspect that to make sure that we know which set of data is for which. But now we have two plots. If you were to do all of them, you want to get the velocity and the displacement. You just have to set those diagonal. So in this case, diagonal term to 1. So that is 0, 1, and that last one would be equal to 1. So that should give you 4 plots. So you hit apply and rerun it again, and you should get 4 plots, which is 2 plots for the displacement for each mass and 2 plots for the velocity for each mass. So let's keep it this way, and let's go to, before we go there, we're going to just to make sure that we get those in array and apply OK, and let's rerun it again. And we're going to go straight to the, let me go to MATLAB. And let's, just to look, if I go open that one here. Wait, what is that here? Let's open, let me maximize this one here. All right, where is that? All right, sim out. So if you look at T out, you're gonna see one value. If you look at sim out or out sim out, you see this is the displacement for the first mass. The second column is displacement for the second mass. This is the velocity for the first mass, and this is the velocity for the second mass. So if you were to plot that, so if you would just do plot T out, T out, sim out, you will get all these plotted in there. Now you can plot just one if you want. So I can just do the, if I do, for example, sim out and just do one here, first column, and let's close this one here and hit OK. So you should be able to get one figure in there, which is the first displacement. You can actually, if you want to do a plot, let's do this one here also, out. Let me just do the same thing I did, but I'm gonna modify it a little bit. So I'll just go do out dot T out. All right, so, and I'm gonna do sim out. I'm gonna do the displacement for mass 2. So I'm gonna just do column, and remember the second column will give me the displacement, and I'm just gonna do this as let's just do this one as broken lines, and let me close that one. Let's see what we get in here. Sim out, T out, out T. Yeah, it is a little bit tricky. You just have to do out, sim out. So out dot sim out. Plot. Let's see if we get that. So you get two plots. Well, let me just do this one as let's do this one as all right. Let's see here. Now we can see. You see that this is the first one, the blue one, and the red one will be the displacement for the second position. Okay, so you can do the same thing for the velocity, and you can actually use a legend for each one, and then you can plot all of them. It would be wise to plot the displacement on one and velocity on the second one, or otherwise you have to make a different y-axis on the right. So you can play with that figure the way you want, use the tools that you want, or can do two y-axes, one for the displacement and second for the velocity, and plot all of them together. But again, this is a great way of solving this problem. Again, it's a two differential, second order differential equations, and they're solved simultaneously using the LTI Simulink system. Okay, so that should be okay. So please do that also and see if you get the same results. Yeah, I was thinking about doing those rank thing. So let's go to sources and see if, I know I've done this before, and let's see if I can find something, I think tools generator or something that I did before. Yeah, it should be somewhere that all right, so we talked about other than using ramps. So let's go to sources and let's do a signal builder. So let me drag this one and bring it here. And now signal builder is easier than having 3 ramps because you can build the signal, because remember you have it from 0 to 1, 1 to 2, and 2 and finish. So you can double click on that. And this is the signal, defaulted signal. So we gotta change this a little bit. So let's do this here first. Let's change this point here. So it is, we want it 0, and yeah, let's leave it at 0 here. But the second point, remember at 1, t is equal to 1, right? So we're gonna change this to 1. First of all, this will be 1, and this will be also 1. Okay, so let's see here. So that will be the first one. It's that. It is that signal which is equal to t. F of t is equal to t, right? And from 0 to 1. Now from 1 to 2, it is 2 minus t. So I'm gonna change this one here to it is actually y0, because at t equal 2, 2 minus 2 will be 0, so that will be 0, yeah, and this will be equal to. Okay, so that would be equal to. All right, so that is ft equal t, and this is ft equal 2 minus t, and the rest is equal to 0 from 2 on is equal to 0. So let me do this one here, and I want to change that to, I'm going to bring it down to 0. So in this case, y is equal to 0 in here. So now again, from 0 to 1, it's ft equal t. From 1 to 2, ft equal 2 minus t, and then from 2 t greater than 2, we know that ft equals 0. So let's save that, and let's see what we got. Let me see what we got in here. So let's minus it in here. So what I'm gonna do, I'm gonna break this, and I'm gonna connect this one back to this and see if we get the same result. So let's rerun it again, and And if you do this, yes, we get the same results. Okay. So you can build it using the ramps if you want, or you can do a signal builder, which is really easier because you really don't have to play so much with the slope. Because with that one, you're really changing slope again from +1 to -1 slope, and the other one you're gonna also do another -1 slope, a +1 slope. So that one will just you build it based on the curve, and then you get uh, the response that you want. Okay, so that is we did the sim out as well, so we should be done with this example. One more example, and then we'll stop for this. So let's see what we get in here. Oh, this is too. Let me delete this here. No, not this one. Oh, I guess we're going to use just this one. All right, so I want to read this, and we'll do that one. Now, I think we should stop afterwards because we've done a lot of problems in Simulink, and I'm hoping you guys also don't limit yourself to the homework problem that I'm giving you. There's in your book also a lot of problems that deals with Simulink. And there's tons of problem online about Simulink that you can do as well. So let's read this one here. For the model shown, and let's see here. Well, I guess I don't have that one. Let me, probably I deleted that one. Yeah, I want to do the PID controller. So let's see if I have that one. Let me do not save that one, and let's go back in here. We open it. Guess I probably deleted it by mistake. Well, I guess I don't have it. Okay, I don't have that figure 10.10.3. With let's read this one. For the model shown in figure 10.10.3 with unit step command input m equal 1, compute. I don't know if this is the one. No, not this one. So compute the PI gains required to obtain the roots, S equal -50, -100, run the simulation and plot the speed. And is the response time what you would expect given the specific roots? Suppose the disturbance is a step function with a magnitude of 100 and a step time of 0.1. Run the simulation and plot the speed, and how effective is the controller in counteracting the disturbance. So first thing first, we have to find that that figure. So 10.10.3. Let's try to find it. And okay, so here we go. This is the figure 10.10.3. This is the Simulink model of the simplest speed control system. And let me enlarge this a little bit to show you what I'm talking about. So we have a desired speed, and we have a PID controller, and this is the step function, right? This is the gain 1 over m, and this is the integrator and the velocity, which is to the workspace. So this is what we want. and we want to see if we can get something similar to what we got. And it's given us some values for the roots for the PI gains required. So we want to first solve that and see if we're going to plot it and see if the response is good enough for us. So the roots he's telling us is minus 50 and minus 100. So the roots, once you have the roots, remember here, minus 50 and minus 100. So that's going to give us an equation, which is plus 50. I'm talking, this is the Laplace transform, x plus 100. So if you do the calculation for this, you're going to get s squared plus 150s plus 5,000. So that is the polynomial for the PI controller. Now remember, the PI controller, if you look back at the lecture, it is M plus D. This is the form of a PID controller, S squared plus PS plus I is equal to 0. And remember, this, you know, when you do this is the integrator and derivative and also the gain. So which is integral, derivative. So all we have to do is just with m, he's telling us m equal to 1, right there, and so with m equal to 1 and set d equal to 0. Well, I didn't say a d equal to 0, but let's just do d because the derivative is 0. Because all he asked for, he says pi, it's not a d, it is a proportional and integrator, so there is no derivative. So d is equal 0 and m equal 1. So that's going to give us s squared plus ps plus I equal to 0. So in this case, the gain will be 150 if you compare this to this. And the integrator, in this case, I will be equal to 5,000. Okay, and so how do we have to really do that? So we're going to have to go back and to Simulink and plot this with this PI. Unfortunately, there is no D component in there, but you know, we're going to see, we're going to try to play with that one as well. So let's go to Simulink and let's try to open a new blank model, and yeah, so that is Simulink. I'm opening too many windows in there, so definitely I have to close some. This is closed. Also this one. So that is the new one that I want, and I'm gonna just do this. All right. So I'm just gonna do whatever they have in there, and then change the PID controller value. So we have an integrator here, and we have a, let's see here, scope here. And or scope or V, whatever you want to call it. And 1 over m, it is a gain. So gain 1 over m, in this case 1. I'm going to leave it 1 because m is 1. I'm going to do a sum here. All I'm doing whatever they that design of that. So that's plus and minus. Minus and plus, sorry, minus and plus. Apply, okay. Let me enlarge this a little bit. So let's flip this. Let's rotate this one. Rotate. Clockwise. I don't think I got it right, so let me rotate one more. So clockwise. No, that's not working. So we want it minus and plus. One more. Clockwise. That's fine. We'll deal with that later in a minute. So, if we go back in here, it says that the magnitude of 100, the step function, but the step time of 0.1. All right, so let's do a step function in here. So that's what is, step function. Step. We said step time to be 0.1 and initial value, keep it 0. Final value, the magnitude, disturbance step function with a magnitude of 100. So initial value 100. All right, so another thing that I want, let me just move this one here. So I'm going to connect this here. All right. All right, and let's connect this one to the integrator and the gain to the integrator in this one here. So that is a minus. So I'm going to just flip that minus plus minus. So I don't plus minus apply. Okay. Yeah, now it's better. And then I'm going to do the PID controller here. PID. And here's some things that proportional. We said 150, P150. And integral is 5,000. 5,000. 0 for the derivative. Apply, okay. And let's do a source. Source maybe. Well, desired speed. Let's just do the source of 1. Block. So it's 2 constant 1 here. So let's connect that. And let's connect this one here. And we are going, before I do that, I want to do, before I connect this, I'm going to do a sum here. So let's move this one here and do sum. Plus minus. don't forget the sign because it gets messy if you start playing with the signs, right? And this one here. And I'm just gonna connect this one to this here. Sometimes, so let's move this one here. So that should be fine. Yeah. All right. So here, so we can see the whole diagram. All right. So let us run this and see what we get as far as if it does. If you see the overshooting in here. Something is not right in there. So maybe something to do with the step function that I have in there. So let us get out from there. Make sure I have everything in there. So 1 over m is correct. ID is correct. Desired speed 1. And let me just do this here. Final is 0. And I apply. Okay. Run it. Let's see here. So this is not what I want. All right, so okay, so this is let's go back here to the step. Initial value, I'm going to put that 0, and final value will be 100, and the step time will be 0.1. I think that should solve the problem. So if you go ahead and run this and see the scope in here, you will see that there's an overshoot in here, which is almost 1.1, maybe something, 1.12. And also there is a disturbance that also caused some drop. And you see here that also almost to 0.5. See, this is 0.4, maybe 0.5. So that disturbance caused that step function disturbance caused some a drop from 1, because again, and then at the end it will go and become 1. And that's what we want, right? We want to be able to whatever the desired speed, which is 1, constant, to also achieve it on the other end. And that's exactly the response based on that disturbance. And remember, the PID will help on that. But there's some disturbance in here, some overshooting, and then some also drop right here. But at the end, after less than a second, I think like 0.2 seconds, if you look in here, 0.3 seconds, everything will be back to 1, the desired velocity. Now, there's other thing that you can do. So if I go back, let me just do this here. If I go back to the PID controller, and there's a good feature which is a tune feature for the PID. So you can actually optimize that transfer function for the PID. So if you hit on tune, and let's see here what you get in here. Main. Let's see if I can. There's yeah. Let's just here see what is the tune. How you can automatically tune it. Okay, here we go. So it looks like it tuned it to P1.028, and so look at the tune response here. So if we really, you'll see that tune response much better than the other response. So it should be fine with this one if you want to see the tune response, and just hit apply. Let's see here. Tune, let's do that. Should just hit apply afterwards. Takes some time to tune, but should be able to get a so let's view this one here. I don't see the apply button. Let's go back here. Owner should be able to just set it OK, and that will give you the new tuning. Right, so when I'm hitting here, I'm getting the response. Yeah, this is the response that I had before, right? So, which I have overshooting, and then I have a drop. So there's a feature in the PID controller. If you go back and let's go to Simulink here. If you hit on the PID controller and if you tune that, it goes and linearizing the plant and will give you a better response. If you look at this response here, so this is your block response, and this is your tune response. Remember, we asked to have one, which is a little bit overshooting, but there's no drop. Now, so that is better than the other one. And if you want, you can you will see that this is way smoother than the other one. But look at the parameters now. We have different parameters. We have P1.028, integrator is 0.1966, and you have a derivative in there. So now we don't just have a PI controller, we have PID controller if you do it, but you get better response on this one. And you can definitely update that if you want, update block. So it will go back and update those values in there. So you see those values are updated for you. You don't have to copy those. All right, so I think that should do it for this chapter. We'll start next lecture with chapter 11. We are going to cover chapter 11 and 12. We will have, we'll also try to cover 13 as well. 13 will not be included in the final, but 11 and 12 will do examples in class. Example will be definitely included in the final. All right, so we'll see you in the next lecture. Thank you very much.